Thank you, Thorsten, and good afternoon, everyone. My name is Meng Xu from Georgia Tech, and I'm happy to present the work on how do we design the dominance scheme for the IoT devices. And this is a joint work with 3 interns, me, Manuel Zhichuan from MSR, and our advisors there, Paul, Marcus, Sanho, Andre, Dennis, Rob, and Stefan. So we know that this large-scale IoT deployment has arrived with the Industrial 4.0 smart city supply chains. So the thing is, like, they have identical IoT devices deployed across like a lot of places. For example, this widely deployed air quality monitor is actually deployed everywhere. You can find the same identical devices a lot of places around the world, around the states. But once the attacker can compromise a single device, they will be able to compromise everything because it's basically identical. They share the same vulnerability, share the same bug. So are we really ready for this kind of attacks? How can we recover those things back, even where they are actually rooted and without too much of manual invention? And so let's think through this with a concrete example. So suppose that your company is tasked to manage all the smart traffic lights across, say, California. And those traffic lights are actually deployed in all the places in California. And they are managed by a central hub called IoT Hub. This hosted on some IoT cloud services. So in normal cases, these traffic lights will be able to send the traffic condition reports to the hub. And then the hub does some processing and then replies with how you are going to schedule the traffic, say in the next couple of minutes or hours. But what if the attacker can exploit a software vulnerability or exploit a weak password there and then control all the devices there? And once the attacker gets there, it will be able to cut down all the services and then basically all the traffic to the hub is lost and is controlled by a botnet. And our only solution probably today is to deploy, say, a batch of service field workers and go there, drive a service car, and fix the things manually, say flush the firmware, or take down the firmware and reload a new one. So can we do a little bit better than this, sending people there to fix all the cameras? Can we do something like we press one button in the administration room, and then we suddenly get all the device back and recover them back into working again? So how can we do that? So this talk is about how do we achieve this. And this is the concept we want to introduce to the IoT world. It's called dominance. So we say that this IoT hub can dominate an IoT devices if the hub can choose arbitrary code and let the device and force the device to run the arbitrary code within a bounded amount of time. So in the example that is hacked by the attacker, the arbitrary code can be the patch firmware, and the bounded amount of time can be, say, within 4 hours of attack discovery. So basically, we want to say that we are able to recover the device back to you within 4 hours of attack discovery. So how do we do that under a powerful adversary? So recall that we assume a very strong adversarial model. They can compromise your application, hijack your communication, and even root your firmware, your kernel. So the only thing we trust here is the hardware, because you cannot reach the hardware from the software level. So we are going to show you that what are the hardware primitives we use to build this dominance scheme. So basically, there are 3 primitives we require. The first one is a read-write latch. So basically, the latch blocks all the read and write accesses to a storage region once you apply there until the next device reset. So basically, once you apply the latch to certain storage regions, no further access to that particular regions, no more. And similarly, there's a writer latch, which is kind of weaker form of the reader-writer latch. So only it blocks the write accesses, but still allow read accesses to the storage region. And the next piece of hardware primitive is called authenticated watchdog timer. So we say that this watchdog timer is similar to a conventional watchdog timer, which we will explain later. But it's similar to that, but instead of you can service the watchdog with writing some constant and publicly known passphrases, this kind of watchdog timer has to be serviced with the certificates issued by the hub. So how do we get there with the 3 primitives? Well, we can say that we can achieve this dominance scheme with 3 guarantees. So the first guarantee is that whenever you hit the reset button, the device will boot into a trusted bootloader, and the bootloader is unaltered. We guarantee that it is always unaltered. even compromised firmware. And the second guarantee says that when this bootloader finishes bootloading the firmware, it will always transfer the control to a firmware that is actually approved by the hub. Which means that if the bootloader finds that the firmware is not actually what the hub wants, it will go to the hub, download a patch, flash the firmware, and boot it. And the last and most important piece of the scheme is that when the firmware is running, and we assume that the firmware is untrusted and can be rooted and can refuse to take command from the hub can still unconditionally force a reset at the device. And when the reset happens, it will go to the CIDR bootloader, which is the trusted code and the code we can control. So that's the three guarantees. But there's also one thing we want to highlight in the scheme is like we try to do isolation in time. So we don't want the CIDR code and the trusted code and the untrusted code to run in parallel. We try to isolate strictly in time. So we alternate the execution of trusted and untrusted code. So we'll highlight this later, but let's see how we achieve these three guarantees first. So guarantee one, we always want to reset into an unaltered bootloader, which is controlled by us. How do we do that? We use the read-writer latch. Sorry, the writer latch. So basically, as we showed you before, it blocks the write accesses to a storage region. So what we do is like on your storage, either a flash or eMMC, we're going to scan what other blocks that your bootloader resides, and we are going to apply this latch right before we transfer the control to the untrusted firmware. So before, and after that, even the attacker control the firmware however you want, there's no way it can compromise the CIDR bootloader. And when you do a reset, it will always come from the unaltered bootloader. So the second guarantee is that we are going to always boot into firmware that is approved by the hub. And for that, we need this attestation and patching scheme. So for attestation patching, we need to communicate with the hub. And everyone knows that if you're going to communicate through an open channel, you need an attestation key. So how do we come with the attestation key? It has to store from somewhere on the device. And it can only be used by the CIDR bootloader because that's when the attestation and patching happens. And it cannot be learned by the firmware running because the firmware is untrusted. And if you let the firmware knows it, the attacker can knows it, and then it can fake the communication between the hub and can hijack this thing. So how do we seal this attestation key? Is to use the reader-writer latch. So recall that when you apply the latch, there's no more accesses to the key. Therefore, we consume the key in the bootloader, and right after that, we immediately apply the latch. Therefore, no more read and writes to the region, and there's no way the compromised firmware can learn it. So another thing is like, because we need to talk to the hub, we inevitably need a networking stack. So, but we want to highlight that this networking stack is not actually part of our TCB. The reason is like networking stack is huge. It can be a lot of implementations, a lot of code, and a lot of attack surface. But this not actually has to be trusted by us. We basically isolate the whole networking stack into a recovery module, and we treat the recovery module as a firmware. So before we actually boot into the recovery, say if you want to talk to the hub, download patches, we treat it as a firmware. We apply all the latches, the watchdog timer, which I'll later explain, and then you do that. So even if you compromise the networking stack, it's just like you compromise firmware. There's no further damage to us. So, and also which is in our paper, we say that you don't actually have to go to networking every time you boot. You only go to the networking, basically only download the new patches if the hub thinks that you are compromised. So therefore, in normal cases, you just streamline into your firmware. And it's only when the hub is questioning the integrity of the firmware, it tries to download the patch from the hub. So the third guarantee is that we are going to unconditionally reset the device if the hub thinks that the device is not functioning very well. So basically, in a normal case, the hub can still try to talk to the device, but the attacker can simply refuse to cooperate. But with CIDR, we want to give you the guarantee that even if the attacker stops responding, you still a guarantee say that you are going to reset in 10 minutes, no matter what. And this is the thing we want to provide with CIDR. But how do we do that? So the first trial we take is to use the conventional watchdog timer, which is very popular among IoT devices, and it was used to as a resilience guarantee to be defend against those buggy IoT firmware that hangs occasionally. So the thing works like this. So when the firmware is running and everything is fine, you will write a constant value to a register or a memory location. So as long as you service the watch-out timer, and the timer will never go to end and never expires. But if you hung accidentally, the timer will expire and it will reset your device. So this is the conventional watch-out timer. But the bad thing is like the attacker can also know this. And once it gets in the firmware, it can simulate how you service the watch-out timer and do this. For example, the attacker can still write the same value to the register or to the memory location. And by doing that, it basically keeps the device forever, as long as it can service it. So the solution is to use an authenticated watch-out timer. So instead of writing simple things to the register or memory, you have to fetch a ticket or certificate from the hub. So basically what you do is you generate a nonce and ask the hub to sign the nonce for you. And then you serve the signed certificate to the firmware. And then by doing so, if you are running and the hub is satisfied, you are allowed to be continue to run. And if in any case that you are rooted and the hub finds out that you are not, the firmware is not what the hub wants, it will stop issuing the tickets and the timer will expire and reset your device. And recall that when you reset the device, it will always go to the CIDR trusted bootloader. And then in the bootloader, you can download the firmware and do the patches. So this is how we achieve the third guarantee, which means that the hub can always unconditionally force the device to reset, so as long as the hub stops issuing you the certificate. So we implement, this is a quite new concept and there's no commodity hardware for do this. So there are two ways to implement it, we show in the paper. One is to use an external microcontroller. So you can obtain them in very low cost, probably less than $1, and write it, program to plug into the serial port, and it will work. Also, you can repurpose the existing hardware if you have trust zone or this Broadcom secure physical timer, or you have memory protection unit. You can repurpose this existing hardware to make it an authenticated watchdog timer. So for details, please read our paper for this. And we prototyped CIDR into 3 boards. Solid round, Raspberry Pi, and STM32, representing high, mid, and low-end boards based on the prices. So basically, how we prototype it is basically read through their menus and find out what are the things that provide the latches or provide the authenticate, what are the primitives in the menu we can use to construct the latch or the watchdog timer. And we found that most of them are quite readily available in those boards. You just need to find the right thing and use them as the latches or the watchdog timer. So in case that they are not readily there or you don't want to repurpose the hardware, you can always obtain it in a very low cost by obtaining an external chip. So so here's our evaluation. So we try to we program CIDR on a bunch of boards, and when we run the firmware that is commonly run on those boards, and we found that there's no compatibility issues. CIDR works pretty well with those firmware. And the evaluation shows that for boot time, in most cases, there's a little bit delay because you need to do this extra cryptography things to verify whether the firmware is actually the thing you want or not. And in the very worst case, you need to go to the hub and get the patch. Then the time actually depends on how large the patch is. So in terms of runtime delay, it's really negligible. The delay is caused by when the firmware is running, you need to periodically go to the hub and get a certificate to feed the watchdog timer. But as we see that the overhead is really minimum because this only happens in practice once per hour or even per day. So it's really minimum. And there's also some discussion and some thoughts we try to put in the paper. So we try to argue that we are providing a solution which is not only minimum in software sizes, but we also want to require a minimum hardware trusted computing base. So, and basically we have 2 thoughts. One is runtime isolation, And the second is isolation in time. So we can easily program CIDR into SGX, for example, trust zone, everything, just put it there. And that will be, and let the CIDR run together with the firmware. And that's what we call runtime isolation. But in order to do that, you need a lot of hardware things. Like you need to multi-threading support. You need this string privilege separation, which we learned from day one as a social norm. And we also need this page tables, this memory management units. And we need to get the interrupt and context switches done correctly. So these things are, if you still remember day one, session one, so these things are subject to side channels, spectral attacks, and many types of attacks on the hardware. But for us, we try to do isolation in time. We don't need those complicated hardware stuff. All we need is some latches, very simple in concept, and an authenticated virtual timer, which you can program in a very small microcontroller unit. And simplicity is really the key to the whole scheme, and it's immune to those speculative execution and side channel leaks. And it's a perfect fit for providing a security cornerstone for the IoT. So you can program your firmware however you want. You can compromise however you want. But there's always a cornerstone you can go back to once it's compromised. So in conclusion, we think that dominance is very necessary in the presence of large-scale IoT deployments. We need a scheme to return those thousands of identical devices back to their original mission. And it's a practical scheme that enforces dominance. CIDR is a practical scheme that enforces dominance on those devices. And it achieves this with three guarantees: booting to CIDR, and firmware attestation, patching, and unconditional reset. And the evaluation shows that CIDR is compatible with a wide range of boards and firmware, and does introduce negligible overhead. And with that, I conclude the talk, and thank you for your attention. I'm happy to take questions.
Okay, so we have time for a few questions. And let me start. How about denial of service attacks?
Yeah, good question. So yeah, many people will think that this will actually give you denial of service attacks. So I have a few backup slides. Let me just pull this up here. Yeah, so yeah, it's a very common question. Like people ask, what if the networking stack gets hacked? Well, the worst case, as you said, is a denial of service attacks. You just boot into this endless loop within this. And the common practice, and also what we propose to do, is for this kind of denial of service attacks, regardless of whether you have CIDR or not, it will happen, because that's against your IoT devices. And for those cases, you have to ask this internet service providers to temporarily block those attacking traffic, and until you come up with a patch and patch everything there. So the thing is, like, we don't make things worse. So if you're subject to denial of service attacks, so that's what you are going to subject to initially. And also, we don't actually make it more vulnerable in the sense that we don't go to random ports or random IP addresses or random domains to ask for device. We only talk to the hub, which is most likely the IP address is hard-coded there. And we only enforce the connection. We only actively initiate the connection. So instead of passively opening a port and waiting for commands. And the very last thing is like, it's an internet of service, internet of things. And if you have denial of service, your original functionality wouldn't work as well. So yeah.
Hi, thanks for your talk. Have you considered that since IoT devices are fundamentally like low power devices, power saving features, like one of them, for example, would be to be able to shut off the eMMC independently of all the others, and therefore if you could, as an attacker, could power cycle it, you could reset the latches. Have you considered that?
Yeah, we actually consider this. We actually find that by programming the pins to certain things, so I mean, it depends on how you wire the eMMC device into the board. So if you wire it correctly, you have to reset the whole devices for this. And yes, I think what you said could be a valid point, that if you periodically shut down the eMMC and then restart it, whether the latches are still there. So if the eMMC latches are not there, probably you need to plug into another MCUs, which you can program in like less than $1, and then plug it there with the extensible UART or serial ports, and then do the protection there. So yeah, so it's really like implementation dependent and vendor specific.
But have you like given major warning signs like you shouldn't implement it this way?
Well, I won't have to put a major warning sign. I mean, as I said, this is really a vendor specific thing, so I'm not so sure like whether we should really broadcasting that you should implement it this way or that way. I think it's up to the user to decide on this.
Okay.
Thank you.
Okay, with this, I would like to thank Meng again.
Thank you.